Hello, in this video I'm going to run through a complicated problem compared to what we've done so far in classical mechanics, and this will then have to use Lagrangian classical mechanics as our way of analysing it. So what I've drawn on so far doesn't look that far away from what we've already done already, but you might be wondering why I put this capital M here on the slope. So let's mix up what we're used to doing, where we just have an object going down a fixed slope, to say, well, the slope is moving as well. Now we've got two objects in motion, and the motion of each object is interlinked. So we've got the slope is moving with a velocity capital V, and then we've got the object moving down the slope with velocity little v, but that little v depends upon capital V because the slope's moving. So we've got an external frame of reference to all of this where everything's being measured from. We're not operating in the frame of reference of the slope, which is pretty much what we've done in all of our problems so far, because the slope isn't moving. Let's think about what we would have to do if we were approaching this in the usual way and we were going to draw out our force diagram. Well, it's not too bad for the block on the slope in itself. I mean, that's still not going to be great, but looking at the slope, we'll have a weight going down. We're going to have a reaction force coming from the ground, but then we've got this extra force coming from the object on the slope, and this force point of application is moving. That's something that we're not used to in Newtonian classical mechanics so far, because as that moves, our reaction force, because this force here is going to be creating rotational motion, so our reaction force is going to be changing in position. Things are getting into a right mess here already. We've also got two different accelerations. We've got one for the slope and one for the block. So we've got variable forces, variable accelerations. The forces and the accelerations are interacting in some way. I mean, it's just immediately getting into some kind of what feels like a nightmare scenario in Newtonian classical mechanics. So what can we do then if we're looking from the Lagrangian approach? Right, we need to first of all look at our dimensions of motion. What things are we looking at? So let's set up a couple of fixed points that we're going to measure things from. So we can measure the position of the slope from this line over here. So that would be, this line here is going to be stationary in our frame of reference. It's going to have something to do with an origin in the frame of reference, but that's where we're measuring from, this fixed line here. So we call that dimension x1, and we can measure the position of the mass on the slope, measured down the slope from the top, and we'll call that position x2. Right, so there are our dimensions of motion. We need to now set up our Lagrangian, which is the kinetic energy minus the potential energy, and then for each dimension of motion, in which case we've got two, x1 and x2, and note that they don't have to be perpendicular to each other or anything like that. These are just the directions that we're measuring things in. For each one of our dimensions in our configuration space, we need an Euler-Lagrange equation. So our Euler-Lagrange equations are the time differential of the Lagrangian with respect to velocity, and that is equal to the partial differential of the Lagrangian with respect to position. So we're going to have two Euler-Lagrange equations, one for x1 and one for x2. So these are the things that we need to set up. Okay, right, this is going to be a lot of work, but the kinetic energy of the slope, that is a half mv capital M capital V squared. So that's fine, but we need things in terms of x1 and x2. So, but our capital V is just the rate of change of x1. The velocity of the slope has got no x2 in it. It's all in the x1 direction. So we can just say that is a half capital M times x1 dot squared. So that bit, fine. Right, so the kinetic energy of the block on the slope, so the kinetic energy of little m, so that is a half little m little v squared, but little v does depend upon both x1 and x2. So we're going to have to do a bit of work here in order to figure this one out. So we've got x2 dot is one velocity. We've also got x1 dot, and it's the combination of those two velocities that gives us the velocity of the block in our frame of reference. So not relative to the slope. That's why we can't just do x2 dot, because that's giving us the velocity of the block relative to the slope, and we don't want that. We want it in our external frame of reference that's fixed relative to this reference line. So we need our resultant velocity, because it's moving both down the slope and being pushed along by the slope. So our little v is a combination of the two. We need to now do a cosine rule on this in order to combine everything. So v squared, so let's leave the half little m out there, and then the v squared is going to be our cosine rule. So that's going to be x1 dot squared plus x2 dot squared minus 2x1 dot x2 dot multiplied by cos, and what is our angle? So the angle we want is the inside, is this big angle inside the triangle, and that is pi minus theta. Pi minus theta. Right, okay, and we know that cos of pi minus theta is minus cos, but let's just save a bit of space on the screen at the moment and leave it at that. Right, potential energy. So we're wanting to look at changes in potential energy. So we don't care about what's going on with the slope, because the slope's just moving in a horizontal direction. There's no change in potential energy there. Our change in potential energy is coming from the motion of the block, and it's all in the x2 direction, because x1 is horizontal, or at least a component of the x2 direction. So the potential energy changing in the little block, if we measure from the top, we set that to be our 0, we're going to be dropping by mgh, and h is x2 sine theta. So we've got mg x2 sine theta. So all of this is going to give us our Lagrangian, because we need to add up our kinetic energies and take off the potential energy. So we can write out our Lagrangian as being a half capital M x1 dot squared plus a half little m x1 dot squared plus x2 dot squared. Let's change that to a plus now, so I can get rid of that pi there. 2 x1 dot x2 dot cos theta. Excuse me. So that is our kinetic energy. Then we have to take off the potential energy. So add on mg x2 sine theta. That is our Lagrangian. So first step done. Now that might seem a lot more complicated than the Newtonian approach, and in some ways it is, but we saw how difficult it is to approach this problem in the Newtonian method. So compared to simple problems in the Newtonian method, yeah, this is more complicated, but that's because they were simple problems. That's why we've been doing those problems, because they're simple and they work easily in Newtonian classical mechanics. This is still not beyond what we can do in maths, though. This is everything we've done so far is still, okay, it's tough A-level maths, but it's still pre-university. We are doing partial differentials in this next bit when we set up these Euler-Lagrange equations, but still, it's not going to be that difficult. Okay, so we need to now differentiate this thing 4 times. because we've got two equations and we have to differentiate it with respect to each velocity and position. So let's do all of these then. So we're going to get so for our first, let's set up our first Euler-Lagrange equation then. So we've got d by dt. Let's go for x1. So we need all of our x1 dots, and we need to differentiate those and treat everything else as a constant because it's partial differentials. So we're going to get capital 1 x1 dot there. We've got this first term here, which is going to give us small m x1 dot. Then we've got another x1 dot here, so that is going to give us a little m x2 dot times cos theta. All right, so that's that bit because we've got no x1 in the last term here. And that is going to be the partial differential of the Lagrangian with respect to just x1, which we don't have in there at all. So that is going to be equal to 0. So that's our first Euler-Lagrange equation. We just need to now do the time derivative of all of this. So we're going to have capital M x1 double dot plus little m x1 double dot plus m x2 double dot cos theta equals 0. So that is equation number 1. Now we need to do this again. So we're going to have, separate that off, d by dt. We need to do all of this for x2. So where's our first x2? We got x2 dot here. So that's going to give us little m x2 dot. And then we've got another one here. So that will give us little m x1 dot cos theta. And we've got no other x2 dots, but we do have a right-hand side because we've got an x2 dot. I mean an x2, not an x2 dot. So differentiate with respect to x2, and that's the only x2 that we've got. So that is going to be mg sine theta. Now we can actually differentiate all of this, and all those m's are going to cancel as well. So we're going to get x2 double dot plus x1 double dot cos theta is equal to g sine theta. So that's our two Euler-Lagrange equations. Now all we've got to do, simple as that, is solve these. And we can solve these simultaneously. It's not as difficult as it looks to solve these simultaneously, or usually isn't. I have tried this question in the past. So from what I recall, assuming I don't make a mistake in my algebra here, it will solve relatively straightforwardly. Right, so let's go then from, if we take, let's call that 2. I've changed colour because I don't want to get too mixed up here. Rearrange 2. Actually, I'm going to do it down here to get x2 double dot is equal to g sine theta minus x1 double dot cos theta, because I want to substitute that into equation 1, and then we can solve for x1 double dot, so the acceleration in the x1 direction. So we're going to get capital M x1 double dot plus little m x1 double dot plus m cos theta multiplied by well, what we've got there, so g sine theta minus x1 double dot cos theta. So we've only got x1 double dots in this. We can rearrange all of this to get what well, to make x1 double dot the subject, the acceleration in the x1 direction. So how many x1 double dots have we got in all of this? We've got an m capital M, we've got a little m, and oh, that should be equals 0. Left that off the end. And then what are our other ones? We've got a minus m cos squared theta, little m cos squared theta, and that is going to be equal to, what have we got that doesn't have an x1 double dot in? It's just this first term from the bracket. So that's going to be minus mg cos theta sine theta. So we've now got, easily enough, an expression for the acceleration in the x1 direction. And that is equal to, well, all of this stuff, minus little mg cos theta sine theta divided by capital M plus little m minus little m cos squared theta. Right, now, before we move on to then just writing out what x2 double dot is, that's quite an interesting answer, because we've got that the acceleration in the x1 direction is, well, first of all, it's negative. So we've got an acceleration that's going that way. And it is constant because the mass of the block and the slope and the angle of the slope are all constants. So this is a constant acceleration in the negative x1 direction. So that's useful in itself, because we've now got motion with constant acceleration. We can integrate this. If we integrate this under certain limits, then we can get the velocity as a function of time. We can integrate it again and we'll get position as a function of time. So this is relatively straightforward now to do two integrals on this. I'm not going to go through it because I don't want to make this video last for days. But we could integrate this twice, and we can say, okay, at time t equals 0, well, the position is at this line with a certain velocity. We've got all our boundary conditions, and we can completely state what the x1 coordinate is of the edge of this slope. And we can say this easily using calculus now. That's a very simple thing that we can do using the calculus that we already know. Right, so let's have a look then at x2 double dot. So x2 double dot is going to be equal to g sine theta, and then add in all of that on. So we've got plus all of this x1 double dot, like the negative bit, because I'm just putting it all back into 2 down here, taking this result that we've just found. So we put all of that in. So what's that going to be like when we combine it? We're going to want to try and put everything over this common denominator. We're going to get a lot of things cancelling, hopefully, here. Let's have a look at all of this then. So we're going to end up getting, oh blimey, I'm just doing a little bit of this on pen and paper because I'm running out of space here on the screen. Yeah, okay, so we've come out with m plus little m times g sine theta. And you'll find this if you run through it. This is not complicated maths. I've not hidden something away here. I'm just putting it over a common denominator and seeing how the numerator cancels. Just run out of screen space. So yeah, we've got this. We've got this as a solution. I'm wondering if there's going to be a better way of writing that, whether it's going to tell us anything. I mean, we've got positive on the top. What have we got going on the bottom? Oh, yeah. So, yeah, again, this must be positive. So we don't need to rewrite it. We've got, because we know that the angle of the slope is between 0 and pi by 2. So this sine theta on the top, we'd have to worry about. So we've got positive on the top. The least we can have on the bottom is capital N. So this is positive. So we've got a positive acceleration as we'd expect down the slope. it's once again constant. So we've got two constant accelerations. Again, we can integrate this and we can get velocity in the x2 direction as a function of time. We can integrate it again and we can get position in the x2 direction as a function of time. So even if we're wanting to look at the complicated motion of the block moving down the moving slope, well, a double integration of this first result here, double integration of that is telling us the position of the slope. Double integration of this is giving us the position of the block on the slope. Well, you combine them and we can say exactly where that block is in our frame of reference. We've got that position as a function of time. And there's no way we were going to be doing that in admittedly a cluttered screen, but using Newtonian mechanics on a single screen. It's complicated, there's no doubt about that, but with the exception of having to take these partial differentials on trust, with the exception of that, this is all pre-university physics. So it's within our capability, and we're just pushing against it with these partial derivatives. It's not simple, so don't think you're just going to go through this and say, oh yeah, I understand how to do Lagrangian mechanics now. I mean, this isn't easy, and it's going to take a lot to build up on. But it's relatively few equations. I mean, how many equations have we set up here? We've got 1, 2 kinetic energy equations, 1 potential energy equation, so that's 3. We combine those into a Lagrangian. So you could say that's just one equation that we've set up there, really. We've set up our 2 Euler-Lagrange equations, and then we've solved 2 equations simultaneously. Complicated algebra, but it is only solving 2 simultaneous equations. Difficult ones, but still, we can do that. So hopefully this has illustrated 2 things. The approach of how we use the Lagrangian, and this is how we're optimizing it. Okay, we don't really know what this means because that is way beyond what we're trying to do. We don't understand the meaning of the Euler-Lagrange equations. But this is the process of what we're going through, and we can see how useful it is. How useful it is to use energy, not forces. We've just used energy here, kinetic energy and potential energy. No mention of a force, no mention of Newton's laws. Just looking at energy and how that has reduced down the number of equations that we've had to look at. We haven't had to look at anything to do with rotation. We haven't had variable forces. We haven't had F equals ma. None of it. Just energy and solving 2 simultaneous equations. So yeah, that's the power of the Lagrangian.